Thanks. So it's a great pleasure to have Masatoshi here speaking today about pessimistic model-based offline reinforcement learning under partial coverage. Masatoshi is a PhD student at Cornell University. He's advised by Nathan Kalus. He's also closely working with Wen Sun, and this paper is together with him, and Nan Chiang as well. His research interests are reinforcement learning, causal inference, and their application to digital marketing. Previously, he completed a master's degree at Harvard in statistics and a bachelor's degree at the University of Tokyo in applied math and computer science. Masa, stage is yours.
Sure. Yeah. Thank you for the introduction, Java, and I'm glad to be here. And today, I'm going to present our work with Wen, and the title is Pessimistic Model-Based Offline RL Under Partial Coverage. First, let me give you the overview of our work. Our setting is offline RL. So the offline RL is often used in like social science or like also more medical science. So comparing to, I think the online RL is more standard setting in RL. So in online RL, the agents, here robots, can interact with the environment sequentially. But in offline RL, the agents in this figure, the robots can only have access to the logged data. So the world generates logged data, and the agents can only use data. But after that, agents cannot interact with the environment. The central question in offline RL is really how to use the existing data in a sample efficient manner. So our goal is learning high quality policies from the logged data, and we don't interact with the environment. So that's a central question. More specifically, our question is as follows. Usually, like in many theoretical RL papers, they assume the offline data is fully exploratory. The meaning of exploratory is, let's see this figure. In this figure, the offline data is on a row, and it's on a distribution over state and action. Exploratory means that this the support of offline data is very large. So so that's the meaning. But of course, like in reality, it doesn't happen. So let's say like in medical science, the state space, let's say like the state space is high dimensional gene data. In this case, since the state space is very high dimensional, so the offline data, of course, cannot cover like this whole state space. So our question is, without assuming that assumption, whether we can still learn good policies when the offline data is not exploratory. So the support, even if the support is very small, whether we can learn. And also, I want to mention that we take on a model-based approach. So in RL, there are two approaches, like model-free approaches or model-based approaches. In our work, we take on a model-based approach. So our assumption is we assume that the model is realizable in the sense that we assume some model class, which can be like neural networks or random forest. Like it can be any functional approximation methods. And our only assumption is realizability of in other words, the specification of the model class. And so I want to say that like we don't assume that every data is discrete or tabular. Like as you know, like in online RL, since the exploration is very like difficult to handle, so people often assume that everything is like tabular. But here we don't assume that kind of assumption, and our goal is really like proposing algorithm which can allow for any function approximation. And let me formalize what is the meaning of the exploratory. So as I said, most of offline IRL work assume global coverage assumption. So global coverage means that the data is fully exploratory. Mathematically, it means that the L infinity norm of d pi over rho is bounded for any policy pi. I didn't define what is d pi, but d pi is an distribution of a state and action induced by a policy pi. I'm going to define it later. And the important point here is you can see like it's for any pi. So basically it means that it's almost saying that 1 over rho is bounded. So this means that the rho covers the whole state space and whole action space. Under this assumption, the previous work shows that the learned policy pi hat, so this is the output policy, and this can compete with the global optimal policy. Mathematically, it means that, so if you see the right-hand side, it says that, first let's define some notation, like pi p star is optimal policy, and v pi is the policy value of pi. And it says that v pi p star minus v hat is small. So this means that a learned policy hat can compete with the global optimal policy pi b star. Okay. Instead, we want to like relax this. We want to like, without assuming this assumption, we want to relax the assumption. So we want to show result under partial coverage. And this means that the output policy can compete with any policies pi, such that like d pi, the infinity norm of d pi over rho is bounded. Mathematically, in other words, this means that v pi minus v pi hat is small for any pi covered by offline data. So that's our goal. Since this concept is very important, so let me like let's see the example. In this example, first, you can see that the global coverage assumption is not satisfied because the blue line is like offline data distribution, and d pi prime is an distribution for pi policy pi prime, and pi prime is not covered by offline data. So in this sense, global coverage is not satisfied. However, still partial coverage, under partial coverage regime, we can still say that the output policy can compete with policy pi. So here, the offline data covers like the d pi in pink. So we can compete with this policy pi under partial coverage regime. But of course, like we cannot compete pi prime because we don't have data on this region. So we cannot say anything about the pi prime. In hindsight, like this result under partial coverage is really like natural. And also, it's really like desired property. But I would say that this result under partial coverage is not so obvious. So I mean, previously, like there were no results so much. And so, do you need to answer do I need to answer the question?
I suppose you will answer it later. And if not, then I will just ask it. It was my question. But like, okay, or we can. I can ask the question if you want.
Okay, yeah.
So my question was that it seems that this concept, global coverage or not, it's binary, very binary. But I don't see a big difference between a big finite value, a very, very large finite value, and an infinite value. Both are bad. So why are we resorting to a binary classification of these policies? And I try to answer, I was thinking about it, maybe it's because in the limit of infinite data, there is a big difference between the two. And I was wondering whether you're going to go there or you have some other answer.
Yeah, now like these two concepts looks really binary, but later when introducing theorem, you can see that these concepts are not so binary. And
okay, so it's just like for emphasis, you are talking about the binarization of this very fluid thing, but it's just really the amount of coverage that you want to emphasize.
Yeah.
Okay. All right. Gotcha.
Yeah, thank you. And I forgot to mention, but the partial coverage is strictly weaker than the global coverage, because if you want to compete with the optimal policy under partial coverage regime, what you need is like the infinity norm is bounded for just like the optimal policy in this partial coverage regime. But in the global coverage regime, like you need this kind of the boundedness for any infinity norm for any policies. So in this sense, the second like regime is strictly better than the first regime because you can relax the assumption. And now let's return to this slide. And this slide is saying that, okay, so we're gonna show result under partial coverage, but previously also there are some results like under partial coverage. For example, like this paper assume linear models and then show PAC guarantees under partial coverage. But this work only works for linear models, but not works for any models. So that's the difference. And I also want to mention like there are several works in the model-free setting, and they show result under partial coverage. For example, like in this area theory seminar, also Jin and also his co-author's work already like is presented. And in 2 weeks later, Kenya and also Kenya will present he and his co-author's work about the pessimistic model-free RL. And of course, like model-based RL and model-free RL are not comparable because the assumptions are different. But also like closely related. So I'm gonna add a comparison like later. This is like, so I'm gonna explain what we will show in this talk. In our paper, we propose a model-based offline RL algorithm called CPPO, and then we show the PAC guarantee under partial coverage, assuming the realizability of the model. Notably, this works for any MDPs, so it can like allows basically any function approximation. The second contribution is we define the notion of the concentrability coefficient. So when defining partial coverage, I use the density ratio like based concentrability coefficient. So the d pi over rho is really like using the density ratio. But if we have more structures for models, this can be replaced with much tighter quantities. For example, like in linear mixture MDPs or like KNRs, which is a generalization of LQRs or other like low rank MDPs, this like L infinity type density ratio based concentrability coefficient is replaced with other quantities. Do you have any questions so far?
No, I think it's all clear.
Okay. From now on, let's dive into the detail. First, let me introduce some notation. The first notation is an MDP, which consists of state space, action space, reward, transition density, and the discount factor gamma, and initial distribution D0. Also, we also assume we have an offline data set denoted by D, and it is a triplet of state and action and next action. And there are n samples. And the DGP is S and A follows distribution rho, and S prime follows P star. S prime follows P star. So P star is a true unknown transition density. And since we don't know P star, we need, Chaba is asking question.
Sure. I was just wondering about, you said that this is an unknown transition density. So the question is whether it's important that it's density or not, or.
Oh, sorry. Yeah, it can be. It's just like distribution. So you are talking.
Okay.
Yeah.
Okay.
Yeah. Thank you. So, and for simplicity, I assume reward function is known, but of course, like it can be unknown. So the extension to the unknown reward function case is very easy. The third quantity I introduced is d pi, and this is a state action discounted occupancy measure under policy pi and p star. And another quantity is v pi p, and this means policy value of pi under transition dynamics p. In other words, it is an expected cumulative reward under policy pi and also p. So the expectation is taken like S0 follows D0 and A0 follows pi and S1 follows P. And if you forget the notation, feel free to ask it later. Next, let me introduce function classes. Since we want to incorporate function approximation, so we need to introduce function classes. The first function class is a model class M. And this is introduced to learn the true transition P star. And another function class is a policy class pi. And this is introduced to learn the good policies. And throughout this paper, I assume this is an unrestricted policy class, so all of them stochastic Markovian policies. Next, let me introduce a standard model-based RL. The first step is just running MLE. So in the standard model-based RL, we need to learn the model. So it can be basically anything, but MLE is the most natural choice. So that's why I use MLE here. And recall M is a function class to learn the model. In the second step, using the learned model, we do policy optimization. So here, argmax is over the policy class, and also recall that v pi p hat means that policy value of pi under the learned model of p hat. So in this learned model, we do policy optimization, and we find the policy maximizing the policy value. And this pi hat has some theoretical guarantee, and it says that the output can compete with the global optimal policy pi p star in high probability. And as I said, this assumption is very strong because it requires coverage for any pi. So we want to relax this assumption. So from now on, I'm gonna introduce our proposed method to relax that assumption. here is our algorithm. We call CPPO Constraint Pessimistic Policy Optimization. The first step is the same as standard MLE, standard model-based RL, like just like estimating p hat using MLE. In the second step, we need to solve constraint optimization, and this looks a little bit tricky. But the first argmax is like taken over the policy class pi, so this part will be fine. And this mean part looks a little bit weird, but let's see it. So first, MD is defined. The MD is like a kind of the constraint set. So it's included in M, and this and each element is close to the learned model in terms of the total variation distance. So you can see there is one. So this is L1 norm, and L1 norm is equivalent to the total variation distance in the continuous setting. So you can regard like this is measuring the difference of the p hat MLE and p in terms of total variation distance. And chi is some hyperparameter, and this is kind of controlling the how large this set is. So if chi is equal to 0, MD is like the singleton, like just p hat MLE. So if chi is 0, this step is just like a standard model-based RL. But of course, like in our approach, chi is not equal to 0. So this mean part is basically doing like pessimistic policy evaluation. So we are choosing the least favorable model in terms of policy value that is feasible with respect to the constraint. And the motivation here is we use pessimistic principle. So in like recent 2 years, there are many like papers like called like using pessimistic or some penalization or something, and it is known that it is very successful in practice. And the intuition is in offline RL, the offline data support is not so large usually. So in this case, like outside of the covered region, we should be more conservative. So when doing policy optimization, we want to avoid exploiting on the uncovered regions by the offline data. And this mean part is really like helpful for avoiding such exploitation. So that's the intuition of our algorithm. Next, let me introduce our theoretical result. Before introducing, first we need to define some concentrability coefficients, and this characterizes like the difficulty of offline RL problem at hand. So C dagger pi is defined like the numerator is the total variation distance of p prime and p, and this is averaged over the d pi. And the denominator is the total variation distance of p prime and p, and it is averaged over the offline data. And also we take the SPRIMA over the model class. The first property is it is always smaller than the density ratio. So this inequality holds always. And another property is it is adaptive to model classes. So if the model class is small, C dagger pi is small either. And also in specific models like LQRs, this C dagger pi has a very like reduced to very natural quantities, as we will see later. Like with this quantity in mind, let's introduce our key theorem. The first assumption is the realizability of the model. And then like in high probability, like this equation holds. Okay, so it's saying that the pi asterisk is a policy you want to compare. And the right-hand side includes C dagger pi star. This is a concentrability coefficient for pi asterisk, which you want to compare. And the M is a cardinality of the model class, and delta is just for like the high probability statement, and the rate is 1 over square root n. So this result is saying that the output policy pi hat can simultaneously compete with any comparator policy satisfying partial coverage assumption, like C dagger pi asterisk is less than infinity. So this is saying that if this quantity is finite, and then as n goes to infinity, the right-hand side error goes to 0. So that's why I'm saying that you can learn pi asterisk. And the important thing is this equation holds like uniformly for any policies without like incurring log pi. Okay, and another thing is, okay, so if let's consider the case like you want to compete with optimal policy pi p star. In this case, you need assumption like C dagger pi p star is less than infinity. Like this is still weaker than the global coverage assumption like this one, because it like requires coverage for any policies. So that's why this result is nice. And also I want to say so I implicitly assume the model class is finite, but even if when M is infinite, we can still get the result using localized Rademacher complexities. And this is just like technical stuff, but we need to use localization argument here. So if we just simply like use Rademacher complexity, global Rademacher complexities, this rate will be like 1 over n to the power of 4. So we will get a slower rate. That's why I said that we need to use localized Rademacher complexities. And then we can get this like 1 over square root n rate. But this is just like a technical stuff, but so it's not very obvious to get this rate. And so let me do some derivation. So actually the derivation is very simple. So let's see step by step. First, let me introduce policy value estimator. So like v hat pi is defined like mean over v pi p. So this is a policy variation estimator, and the output is defined just like optimizing this policy class. So argmax is taken over the policy class pi. And then we can show that true transition dynamics is included in the constraint set in high probability. So this is basically saying that the policy value evaluation estimator is always pessimistic. So recall v pi p star is an policy value of pi under p star. So this is a true policy value for pi. And I'm saying that the policy valuation estimator is always smaller than this quantity. So this is like key equation. And then the regret you want to show. So the left-hand side is the one you want to bound, is upper bounded by the right-hand side. And the important thing here is the right-hand side only like includes pi asterisk you want to compute. So then the right-hand side is bounded by performance difference lemma, and then the proof is done. So basically, like the important point is right-hand side does not include pi hat. So if we just like use standard model-based RL, the right-hand side includes pi hat, and that's why we use like global coverage assumption, because we need like the kind of constrainability coefficient for pi hat, but pi hat is a data-dependent quantity, so it can be like any policy in the policy class. So that's why like the error will like depends on like the constrainability coefficient for any policy, but because of pessimism, we can say that this only depends on the pi asterisk. So the policy you want to compete. So that's like the intuition of the derivation. Okay, so next, let me introduce some implication. So as I said, the error in high trouble.
Right. So can we just go back to the previous slide? Um, so this intuition about the derivation, at the end of the day, though, like you want this inequality to hold for any pi star, so that kind of still seems to suggest that you have to control uniformly over the policies this quantity.
Yes.
But of course, you're controlling it because you're controlling the errors for the model in a way, right? So I think that maybe the next step, that this is somehow really simply related to the model error, that's like a crucial step in the proof, and that's like a really interesting step as well, which you are hiding, which you say, oh, performance difference lemma, we know how that works, good.
Yeah.
But somehow you want to bring in this coefficient, and then okay, I guess you use Cauchy-Schwarz or something like that. I don't know what's happening there, but you have to do things.
Yeah. Many things are hidden. Yeah, in this slide. Yeah, that's
Right.
true. Yeah.
Okay. So, but I felt that it's like maybe it doesn't give a just to this argument if you say that, well, pessimism, what it buys you is that you don't have to have a uniform result, but you actually want to have a uniform result, the uniform control. It's more like if you didn't use pessimism, then maybe you would have another union bound or something like that, like on the top of everything that is happening here. And it would be just hard to get away from that. It's kind of hard to say, but yeah, like there's a gain here.
Yeah.
Okay.
We don't take union bound for the policy class, but that's very important point, because if we take the union bound for the policy class and then the log pi appears in the bound, so that's not good.
Yeah. Although I'm wondering whether if you pushed really hard, something like not a pessimistic approach, where you could get some similar bonds.
I see.
They would not be identical, but maybe some other quantities would appear or something, but you push really hard to avoid this union bond, and maybe you can use localization and whatnot in some other ways, and then get something that...
Yeah, I agree. There might be other way either. Yeah.
Okay. All right. Okay. Thanks.
Yeah, thank you. So let me go back to this slide. And so here the message is we take a model-based approach, but we can also take a model-free approach. And for example, in 10 years, very great paper, they show the partial coverage result under the realizability and Bellman completeness of Q function class. And in this case, the policy class, needs to be generally restricted. But in the model-based setting, since the policy and the model are totally separated, so we can allow the unrestricted policy class. But in the model-free case, the Q function and the policy class are not usually separated. So that's why it's very difficult to allow any policy class. So that's the difference between model-based and model-free approaches. And also, I want to mention the difference between our work and also existing pessimistic model-based algorithms. In CPPO, we use MLA guarantee, the total variation distance over the offline data. And in the other papers, this is also our paper, CUSKS. And in this paper, we assume linear models. And then we can get the distance, we can get a guarantee that the distance of P hat and P star is bounded for any S and A. So this is point-wise errors guarantee. So and of course, average error guarantees are weaker than the point-wise error guarantees. But actually, average error guarantees are enough for the pessimism, and it can be obtained for any nonlinear models. So it's not restricted to linear models. So that's why our result is very general. Okay. Finally, I'm gonna introduce several examples, and let's see how the density ratio concentrability coefficient is replaced with tighter quantities. So as I said, C dagger pi star, so pi asterisk is very abstract. So that's the model-based concentrability coefficient which we introduced. But of course, it's not interpretable. So we want to replace this constant with more interpretable quantities and also tighter than the density ratio. The first example is linear MDP. In linear MDP, P star is mu hat S prime times M star and times phi SA. And phi is a D2-dimensional vector, feature vector over state and action, and mu is a D1-dimensional feature vector over the state space. And we don't know M star here, so we need to estimate it from the data. And we can run MLE, and we can estimate M star. And so I'm going to introduce the Pack bound on these models. But before doing that, let's introduce the concentrability coefficient for linear MDPs. So this is written in the this equation. So this looks a little bit complicated, but actually it's just the relative condition number for two matrices. In the numerator, it includes a covalence matrix. So phi is a D2-dimensional vector, so it's the covalence matrix. And this is a covalence matrix corresponding to pi asterisk. This is a comparator policy. And the denominator includes a covalence matrix over the offline data. So it's okay. And then the first property is it's smaller than the density ratio. That's good. And the second property is in tabular MDPs, it's equal to the density ratio. So yeah, and intuitively, this is saying that if C bar pi asterisk is small, this implies the offline data sufficiently covers the subspace that compares the policy pi asterisk visit measured by phi. And I'm not sure this is very interpretable, but in offline RL, people often assume that this offline data covalence metrics, I mean the covalence metrics measured by, the average by rho is full rank, or the least eigenvalue is lower bounded by some constant. So in this sense, like this assumption is still very natural. And this is our result. And here we are saying that if the comparator policy, pi star, so the C by pi asterisk is bounded, and then we can compete with this policy. So the partial coverage concept is defined as like C bar pi asterisk is less than infinity. And the important thing here is this assumption is weaker than the assumption like this matrix is singular. In previous offline RL works, many papers assume that, for example, like this matrix is this matrix is non-singular. But here, if you see the definition, even if like this matrix is singular, if also the numerator's matrix is singular, and then still it can be fine. So in other words, it allows for possibilities like this offline covalence matrix is singular. So this is like the kind of partial coverage on linear models. And yeah, we like quantify the concept of partial coverage on linear models. And I don't think we have time, so I'm gonna skip. But in this slide, I show that on linear mixture MDPs, so this is another model which includes linear MDPs, and we show that on this linear mixture MDPs, we can also like define the concentricity coefficient rather than density ratios. Another example is KNR. KNR is a generalization of LQRs. So it says that true P star is a Gaussian distribution parameterized by W star times phi. So here, W star is an ds to ds by d matrix, and phi is an d-dimensional feature vector. So phi is known, but W star is unknown, so we need to learn it from the data. And by learning MLE, of course, we can learn W star. Okay. And this model is very general because it includes LQRs and also it includes Gaussian processes. So in other words, if the mean belongs to RKHS, and then like we can still like, so this is I'm saying that RKHS models the mean belongs to like RKHS poles. So that's like RKHS models. And for KNRs, let's introduce the concentricity coefficient. And you can see that this is exactly the same as the one in linear MDPs. Okay, so it's again the relative condition number for two matrices. And here is a result for KNRs. First, let's introduce covalence metrics for the phi, and you can see that this says that like we can compete with pi asterisk such that like C by pi asterisk is less than infinity. And another good thing is, again, like sigma low can be singular. And the error in the right-hand side only includes rank of covalence metrics, but not D. So this means that D, the original dimension can be still infinite, as long as the rank of covalence matrix is low. So this is really in contrast to the online RL result, because in online RL result, the dependence on D is basically unavoidable. But here, because we are considering the offline RL setting, so the error can be distribution dependent. So that's the difference between online RL result and offline RL result. Okay, and so formally, we can also say that D can be infinite by using RKHS theory. The third example is low rank MDPs. So let's define. Here the true P star is mu star transpose and phi star. And mu star is an unknown feature vector over the state space. And phi star is also the unknown feature vector over state and action. Since features are known, we need to set the function classes. So for example, we need to assume psi, mu star is included in psi and phi star is included in large phi. And low rank MDPs include many models, like latent variable models or block MDPs or linear MDPs either. And some people call low rank MDPs basically linear MDPs, but I want to emphasize that here low rank MDPs are different from linear MDPs because I don't assume that features are known. So the challenge here is we need to learn really features from the data. Okay. So next, let's introduce a constant coefficient for low rank MDPs. And this is again the same as one we saw, but I want to emphasize that since pi star is unknown, so that's why there's a subscript pi star, and it doesn't depend on the other features. Okay, so and by using this constant coefficient, we can state this theorem, and it's saying that we can compete with any policy satisfying this partial coverage assumption. So partial coverage is defined as C pi asterisk and phi star is less than infinity. And again, the error only includes the rank of the covalence matrix defined on the true feature instead of D. So there are several online RL papers on low rank MDPs, but in these online RL papers, the error includes D. But here, D can be replaced with the rank of the covalence matrix. So that's very good. And also, there are previous related works on sparse linear MDPs, written by Botel, and also I think Chava is also in the author. But I would say that our result does not imply their result, but their result also does not imply our result, because in my understanding, they kind of assume that the non-singularity of any feature covalence matrix for phi in some sense. So yeah, that's the difference. And I don't think I have time, so let me skip factored MDPs. So finally, I want to say the meaning of any MDPs. So we claim that CPPO works for any MDPs, but of course, any means that not really any. So any MDPs means that where the MLE has valid statistical guarantees. And unfortunately, CPPO does not work on for example, linear MDPs introduced by Chi-Jin and also his co-authors, or linear Bellman complete MDPs. Because in these MDPs, MLE doesn't work basically. So that's why on these models, we need to use a model-free approach. And I think the Kenyan and his co-authors paper can solve these problems. But on this, okay, so I also want to say that by taking a model-based perspective on these models, and by modifying the loss function, we can still ensure the pub guarantee under partial coverage. Okay, so here is the final slide. So let me conclude. The first point is we show CPPO has a pub guarantee under partial coverage, assuming the realizability of the model. And notably, this works for any MDPs. And I also show that partial coverage concept is tailored to each model. So for example, KNRs and linear model, linear MDPs, this is written using relative condition numbers. And in low rank MDPs, where the features are unknown, we can also write a partial coverage using relative condition numbers defined on the true unknown features. And I didn't show it in the interest of time, but in factored MDPs, we can also get very good results, like the density ratio can be replaced with the special density ratio for factored MDPs. Okay. And I also want to, so this is just feature directions, but I didn't show any lower bound result, and I don't know how to get it, but I think the lower bound result will be very important to understand how our result is really tight. And in the tabular case, I saw Min and also Yushan's paper introduced some type of lower bound result, kind of incorporating partial coverage assumption. So that's, but still for general function approximation, I don't think there is a lower bound result yet. So that's our future work. And another future work is, of course, our algorithm is not computationally efficient. So we are thinking the computationally efficient algorithm, which has also pub guarantee under partial coverage assumption. Yeah. Thank you very much. That's all.
Thank you. Right on time. Okay, I can start with some questions. I got a little bit confused at the end about this many versions of linear MDPs. In particular, you said that, and looking at the definition of low-rank MDPs, it seems that that includes the Chi-Jin style of linear MDPs. So
Okay.
can you?
Let me see.
Right.
Okay.
So the low-rank MDP, you do have some results for that. And if you take the Chi-Jin style of linear MDP, that has only these two factors, then wow, that's of this type. And you said at the end that your result doesn't apply to those type of linear MDPs. So now I'm really confused.
Okay. So yeah, that's very, I think, confusing point.
Okay.
Yeah. So okay. So this low rank MDPs include linear MDPs for Chi-Jin's linear MDPs. That's
Okay.
true. But at the same time, our results does not cover that case.
Yeah. If you go to the next slide, I think that we will see it. Or yeah, this slide.
Yeah, this result does not cover because in to incorporate so we assume that model class is finite, but to in Chi-Jin's linear models, basically mu part is non-parametric. So the statistical complexity for this phi is infinite. So in his models, phi star is known, so that's fine. But mu star is kind of, how to say, the constraint on mu star is really I don't know how to like write it down very
Okay, so
clearly.
let's keep it simple. So let's say the state space is just finite,
Mhm.
right? I mean, you prove this result, but you prove the result for the case when the number of models is finite. So
Yeah.
one suspect that there is a covering number that appears there.
Mhm.
If you want to extend this to the infinite case. And I guess what you're saying is that yes, you can have this result, but the number of states is going to appear there, and that kind of kills everything, right?
Yeah, yeah,
And
yeah.
whereas for the linear MDP case, if you go like choosing style linear MDP case, if you go with some other ideas, not model based, then the number of states is not going to appear, and that's what you meant, I
Yeah,
guess.
yeah, exactly. Yeah.
So you
Yeah.
can cover it, but it's like a bit
Your pain
meaningless.
states, right?
Huh?
Yeah. Your pain number of states. I wonder if
Yeah,
I
yeah,
just thought about it is like, is that real? I mean, like the analysis definitely shows that if you do a very, straightforward or naive covering, you will pay S. But do you think the algorithm, if you actually literally run that algorithm, do you run into these overfitting issues? Or
Mhm.
actually maybe the algorithm may be fine, or it's just the analysis is loose?
I guess it's a question of psi, right? So that's the parameter of the algorithm.
Yeah,
And if
I
you,
guess I guess what I mean is that what if you just run the algorithm with psi being the tabular class? Uh,
uh,
I guess maybe you're running into trouble, probably.
yeah, psi is going to be set based on the number of states in this case.
Yeah,
So
you
it will be very conservative. But like I let Masa
yeah.
answer this. So, but okay, so I can ask a follow-up question to your question, which is that maybe you can adapt psi in this case, and you could still run a model-based algorithm, which would, I don't know, like do some peering or like some clever tricks of tuning psi in an appropriate manner to avoid this dependence on number of states.
Yeah, yeah,
Have, have you thought about that?
yeah. I thought about that, but
Okay.
yeah, in the end, I didn't figure it out how to do that.
Yeah,
But
I think
yeah, it must be possible.
some ideas like looking at. I mean, one general way of doing that. I mean, we did this basically in the Marful paper where Aditya presented in the seminar. Basically, one possible approach is to look into your model-based analysis and look at what kind of value functions in the next step you're going to back up using mu, right? Then essentially your estimation of mu star only needs to be accurate regarding those backups. That may be one way to get around this issue, but that's one possible way of doing it.
Yeah, so in the context of this algorithm, this would mean that, okay, linear MDPs, all the value functions are linear in the features. And so if we only need to reason about the value functions somehow to figure out the hypothesis, then maybe the covering argument could be adjusted to take this into
Yeah,
account.
but Masa and Wen's paper, this paper, they heavily relies on TV error bounds for the model, so it doesn't quite.
Not this paper,
Yeah, not
but
this paper.
the next
So,
paper. So,
uh,
Masa, have you thought about this too? Like the exploiting the structure of the value functions somehow in the argument, like as a next step?
Yeah, yeah, yeah. And that's why I said that, like, uh, for example, we take kind of model-based approach, model-based perspective on linear MDPs, we can still like get a guarantee. I'm saying that if we run MLE, we can get a total variation guarantee, but because it's hopeless on linear MDPs, so but still like we can take some model-based perspective on linear MDPs. So by changing loss function, so that like as Nan says, uh, like the kind of discrepancy distance for the value function class, and then like we can still like get some type of result. But this kind of result is almost the same as like the, how to say, the algorithm by Tanyan's paper, essentially. So that's why I, I yeah, didn't specify here.
Which paper?
Oh, Tenyon and his co-author's paper, like he will present in 2 weeks later.
Okay.
Yeah, like Bellman consistent
Yeah.
perspective, something. Yeah.
Yeah. Uh-huh. And that paper actually applies to linear MDPs.
Right.
Yes.
The
Right.
cheap instead. Okay. Cool.